Good afternoon. I'm Saritha Kumari, Assistant Professor, working in Institute of Aeronautical Engineering College, EEE Department, Hyderabad. Today the topic is medium transmission lines and its performance. This is mapped to course outcome 3. This is 3, course outcome 3. So basically, in my last lecture, we have seen about the performance of short transmission lines. We know that short transmission lines basically the operating voltage is less than 20 kV, okay, and their line length is up to 80 kilometers. 80 kilometers. So in short transmission lines, the effect of capacitance, the line capacitance effect is neglected, okay, because of the reason that smaller lengths, okay, and the operating low voltages, their operating voltages are, okay, less, okay, in transmission lines, which is given as up to 20 kV. So that's why, that is the reason the line capacitance effect is neglected, okay. Only the resistance and inductance, line resistance and line inductance effects are included, okay. Now look at the second point. But in order to obtain accuracy, okay, accuracy in medium transmission line calculations, the line capacitance must be considered, okay. In medium transmission lines, we know after short lines we have medium lines, okay, where the line lengths are given from 80 kilometers to 160, okay, and voltages are greater than 20 kV. There, for better accuracy to estimate the performance, okay, to estimate the performance, that means efficiency and its regulation. So the line capacitance must be considered. So here, look at the third point. The capacitance is uniformly distributed. We know that the line parameters, okay, RLC, are uniformly distributed over the total length of the line. But in order to make the calculation simple, we take instead of distributed parameter, we considered it as lumped parameter, okay. That's why here, in order to make calculation simple, the line capacitance is assumed to be lumped, okay. That is also nothing but concentrated, okay, in the form of a capacitor which is connected in parallel with the line, okay, at one or more points. The capacitance effect is considered in parallel with the line, that may be considered at one point, okay, or one or more points along the line, okay. We'll see there are commonly they use in methods are to estimate this performance. There are 3 methods: end condenser method, nominal T method, okay, nominal T network, nominal pi network. So these are the 3 methods for the medium transmission lines, okay, they considered to calculate the performance, to estimate. So first, end condenser method. So end condenser method, in the name itself it is there. So the total capacitance, okay, we know that a transmission line like this, one is okay, there are 2 lines, okay, this is sending end and its corresponding current is sending end current. At the load side, this is a receiving end voltage and this is a receiving end current. So the total line resistance and inductance are X, which are considered in series, and the capacitance is considered at the one place, usually at the load side, okay. That is a end condenser method, okay. You can see on the diagram, actual diagram on the slide. So that is how it is represented. So we know that the phasor sum of R and X, okay, we say it as impedance, right? So that's why it is written as Okay, like that. Then the capacitance. So we know that the capacitance is, okay, whose value is C, capacitance. Its reactance is given by 1 by J omega C, right? So that is a reactance, okay, XC. So now that means ZC we say, okay. Now for simple calculations, instead of considered it in the reciprocal form 1 by C, they consider for simple calculations, they want to show it in the numerator. So we know that admittance Y is given by 1 by Z. So that's why for capacitance reactance, they considered it as admittive, okay, in the form of admittance. So they write it as Y is equal to, okay, instead of writing Z is equal to 1 by J omega C, they write it as, okay, instead of Z is equal to 1 by J omega C, they, for simple calculation, they write in terms of Y, that is equal to, in terms of C, J omega C. So that is the end condenser, okay, or end capacitor method, okay, for the medium transmission line, the circuit, equivalent circuit. So the load impedance is ZL, here it is shown. Okay, now what we want? We want to get the expressions for Vs, and we want to write the expressions for Vs and Is, okay, by drawing its vector diagram, okay. You see it on the right side, its vector diagram. So then write down the Vs and Is equations in terms of, okay, load voltage and load current. What is that? VR and receiving end voltage, okay, and current IR. So first, so we know that generally the load, that is the reason, right? Why? Because generally they give the load data, so that's why they start with VR reference. So VR be the reference here, receiving end voltage, okay. So that's why it is taken horizontally initially. VR be the reference, and take load is always, okay, common existing loads are lagging, inductive loads, lagging load. So draw IR, okay, draw IR at an angle, lagging angle, okay, pi r, okay. So IR is drawn at lagging angle pi r, okay. So that is the first current IR is shown, okay, on a reference vector VR by showing angle, lagging angle pi r, IR also shown. Next, so from this diagram, what we will write, okay. So see that we want to write down the IS, okay, and we want to write down IS and VS equations, right? So already we have shown IR, okay, on VR. So first let us write IS. It is easy, right? So from the circuit, okay, IS is given by what? IC plus IR. IS is given by IC plus IR. So already IR is shown. Now what is IC? What is IC? So we know that because it is across the load, IC is given by, okay, with respect to VR. Okay, IC current leads VR by 90 degrees. So this is IC. It leads VR by 90 degrees. So and also from the circuit, the phasor sum of IC plus IR is given by IS. Okay. Okay. So just to look at the equivalent circuit, draw step by step. Okay. Draw the vector diagram, at the same time write down the equations. Which equations? Vs and Is equations. Okay. So first look, is it are we able to write Is or Vs first? So here we started with VR reference. Okay. IR is drawn lagging. Then from the circuit, we say that IS is given by IC plus IR. Okay, IC plus IR. So IR already marked. So draw IC also from the VR. So add these two, IR and IC, okay, to get IS. So draw a vector parallel, okay, from the tip of IR, draw a same vector IC here from the tip of IR. So that's why IC is shown here, okay, because we know that IR plus IC is IS. Now, so that is what it is shown. The sum of phasor sum of these two IS. Okay. The same thing it is written here also. IC plus IR. What is IC? We know that. That is with respect to VR. Right? IC is given by VR into Y. Right? VR into Y. Right? So that is what is it is written. Okay. Finally, IS equation is shown in terms of VR and IR. So IS equation, we got it. Okay. So that is our intention. We want to get the equations Vs and Is in terms of VR and IR. Finally, write down the ABCD parameters. ABCD parameters. Then check the two conditions. Okay. For the ABCD constants, what are the two conditions? Okay. That's the next slide. Okay. Then I will explain there. So here IS is obtained. So that is, okay, IS is shown. Next, what is VS? What is VS? VS is given by IS into this impedance, right? From the circuit only. IS into this impedance plus this. What is the voltage here? Voltage across this parallel path is VR, right? So, because there is no impedance here, further impedance. So, Vs is given by Is into impedance Z, that is R plus Jx plus Vr. So, complete the vector diagram also. Already Is is obtained. So, Is is obtained. Draw a vector parallel to, okay, with respect to Is. Show the resistive drop from the Vr, right? From the tip of the Vr. Draw the ISR and ISX. Okay. So that is how these two vectors are shown. So finally, okay, after obtaining IS, show ISR. After obtaining this IS, so show the ISR from the tip of VR and ISXL. Okay. So resistive drop and inductive drop. So the phasor sum of these three, what we will get? So that is from the equation, we will get Vs, right? So finally Vs is obtained. Okay. So that is a end condenser method. That is a end condenser method. Okay. Equivalent circuit, phasor diagram, and its Vs and Is equations. Now it's ABCD constants. Okay, efficiency regulation. It's from the equivalent circuit only we do. Okay, so we basic definition we know efficiency. Okay, regulation is drop in voltage, right, from no load voltage to full load voltage. Okay, to the ratio expressed as a percentage of no load voltage. If efficiency is output power by input power. What is output here? Power across the load at the receiving end. Okay, and input power is nothing but from the sending end with respect to the sending end. Generally, receiving end power is known, load across the load, that is a given data. So that is what generally P. So input is given by output load power plus losses in the line. Okay. So that is how efficiency calculated, and regulation also. Okay, we will do the problem, then it is more easy to understand. So ABCD constants also we need to see once, okay, as I mentioned already. Then only we come to know for ABCD constants, we have two conditions, right? A is equal to D and AD minus BC is equal to 1. So these are the two conditions, okay. After writing the VS and IS equations, we need to check. Then only we say that the equations written are right. Okay, now. So we know that from the previous slide also we know Vs is given by VR plus impedance into, okay, Is, right? And Is is given by, so this is Vs final equation, this is Is final equation. So what is Is? Is is given by IR plus, okay, Y into VR. And Vs equation is, this is Is equation, this is Vs equation. Previous slide, from the previous slide it is rewritten. Okay, so Vs is given by 1 plus Yz into Vr plus Z IR. Okay, so we have to, okay, with these are the two equations. So the equations written in terms of Vr and IR, okay, and coefficients are in terms of Yz. Okay, so compare the standard format of equations. So these are the standard form of equations, Vs Is equations. So A is what? So what is A? VR coefficient 1. Okay, 1 plus Yz, right? A is 1 plus Yz. And what is B? IR coefficient Z. Okay. Then Is equation. From the Is equation, what is a C value? Y. D value is 1. So check once. Okay. So check once. Okay. So see that this is a condition we need to check. AD minus BC is equal to 1. So so what is the AD minus BC? So calculate that. AD means 1 plus YZ minus BC means minus YZ. So YZ get cancelled. This condition is satisfied. Okay, this condition is satisfied. So from that we say that the derived constants are right values. Okay, so from end condenser method, the derived constants are right. So that is about the end condenser method. So here in matrix form, the above two equations are written. Okay, matrix form. Next, second method, next nominal T. Nominal T network means the equivalent circuit, it looks like in the shape of T, okay, alphabetical letter T. So here, see that the total capacitance is assumed to be at the middle of the line. At the middle of the line. So that is why it is shown like this, okay. So, and it is considered in the form of admittance again. So that's why J omega C is equal to Y. Okay. Now, at the sending end, receiving end, voltages, currents are shown. We already know VR and IR, and sending end Vs and Is. And here, nominal T method, the total resistance and reactance are divided into half and they placed at both sides of the line. The total resistance and reactance are divided into half and they are shown at both sides of the line. So here look here. So the total resistance is, okay, R by total resistance is R, right? So R by 2, okay, R by 2. One R by 2 on the sending end and another R by 2 at the receiving side. And similarly X also. Total X is divided into half. So X by 2, okay, at sending end, another X by 2 at receiving. So what is the total impedance here at the sending end? R by 2 plus JX by 2 which is nothing but Z by 2. Okay, Z by 2. This is also another Z by 2. Okay, so the impedance in the nominal T method. The total impedance is divided into half and total capacitance is concentrated, assumed, okay, to be concentrated in the middle of the line. Okay, now what is the reference here? It's the same manner. Okay, draw the vector diagram, phasor diagram, and write the equations for Vs and Is. Okay, in terms of VR and IR. Okay, then ABCD constants. So taken VR be the reference again. Okay, it is small or it is shown. Okay, it's not a matter, we can take, okay, either small or a capital R. VR be the reference, and here see that it is taken like this. VR, not horizontal, they have taken, okay, a slant vector. It is just for the convenience of the diagram. Okay, to draw in a convenient manner the vector diagram. They may take horizontally or little bit, okay, in a slant manner. So here nominal T method it is taken little bit, okay, it is VR reference vector taken like this slant vector. So same manner IR assumed to be lagging load. IR lags, okay, so this is a IR lagging angle, okay, it is shown. Okay, now look at the diagram. So again we want to write Vs and Is, right? So it is first better to get Is. Okay, so from this diagram, what is Is? What is Is? So Is is given by voltage, current in the capacitor plus receiving end current. Okay, so Is is given by IC plus IR. What is IC here? So what is IC here? Okay, current in the capacitor is nothing but now voltage across the capacitor, right? Multiplied with its reactance. Okay, because we can't say that is with respect to VR directly because there is a resistive drop here. So there is a capacitive voltage present here, which is VC. So IC is given by VC into J omegas, right? VC into Y. Okay. Now, what is VC? Okay, IS equation only in terms of VR and IR. Now, we have VC here. Okay, we want to write this VC in terms of VR from the circuit. From the circuit again, VC is given by voltage drop across this, okay, plus VR, right? VC. VC is given by voltage drop here plus VR. So VC is given by, okay, IR into Z by 2 plus VR. Okay, so that is how it is IS equation first. Okay, complete the vector diagram also. So VR and IR is shown. Then what is after that what we can do? Okay, what we can do next? VC. We have to show VC. How VC is obtained? VR plus voltage drop in this path. Okay, so show the voltage. This is IR, right? So IR R by 2. This is IR R by 2. IR X by 2. Okay, add this VR to the IR R by 2, IR X by 2. We'll get this VC. Okay, so VC is obtained. Then draw the IC. We know that in case of Okay, first step is over. Okay, addition of VR and IRR by 2, IRX by 2 will give us the VC. Okay, this is VC. VC. Now, draw IC. Okay, then we'll write IS. We'll show IS. So, we know that IC lags by 90 degrees, right? Assume perfect capacitor. So, with respect to VC, draw IC like, okay, at an angle of 90. Okay, this is 90. Okay, with respect to VC. So, now, we know that from the diagram, IC plus IR. So, IR is here, tip of IR. So, draw a vector parallel to IC. This is IC. Okay, this vector is shown here. Okay. So, IR plus IC gives us IS. So, IS is obtained. One equation is obtained. Now, what is VS? VS is given by IS into this drop plus VC. Okay. So, that is what it is written. Substitute for VC already we know. Okay. So, finally we'll get, okay, this is the equation. We'll get the VS also. Only in terms of VR and IR. So, VC added to IS drop, right? VC plus IS x by 2. What is the current in this branch? Okay. Here we have AC, VC. Add this drop will give us VS. So, IS R by 2 plus, okay, this is IS for us, right? This is IS. This is IS. Okay. Okay, this is IS. So, parallel to that, IS R by 2 and 90 degrees at 90 degrees x by 2. So, VC plus this drop will give us VS. So, that is a vector diagram and writing the equations. So, now ABCD constants. So, calculating efficiency regulation, standard equations only. We'll do a problem, then it will be more clear. So, from the equivalent circuit, okay, first IS equation. So, IS is given by IC plus IR. What is IC? VC into Y. What is VC? IR into Z by 2 plus VR. So, that is what it is written. So, finally, equation is in terms of VR and IR. Next, VS. VS is given by IS into this drop plus VC. IS into this drop plus VC. What is VC? Already we know, right? VC is given by this drop plus VR. Okay, already we have written up. VR plus IRZ by 2. It is substituted. Finally, write down, simplify the equation only in terms of VR and IR. So, this is the equation. So, compare these equations with standard equations. So, those are the two standard equations, right? PS is equal to AVR plus BIR. IS is equal to CVR plus DIR. So, comparing those, okay, A value is given by 1 plus YZ by 2. B is, okay, that is the equation, right? So, previous. So, B is given by Z into YZ square by 4. Take Z out. So, if we take Z common, Z into 1 plus YZ by 4. So, that is what it is written. Z, they are taking common, and C is equal to Y and D is equal to 1 plus YZ by 2. So, matrix form, put that in matrix form. Okay. We know how to write these two equations in standard form. Okay. A, B, C, D. So, checking the conditions. Okay. A is equal to D. A is equal to D. Yes, both are equal. And AD minus BC. Check another one, AD minus BC also. So it is okay. Finally simplified, a plus b whole square formula it is. So it is obtained as 1. So the constant obtained above are right. So that is the nominal T method. So these are the two references, okay, which I have taken this properties. So okay, this is the end of my lecture now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.